This is Walter Cronkite speaking. We are witnessing in our first picture one of the biggest splashes in history. The date is January 21st, 1954, the place Groton, Connecticut. As the USS Nautilus slips down the ways into the Thames River, not just a ship, but a new age is being launched. The age of the atomic submarine and the Polaris missile. The Nautilus weighs more than a World War II destroyer. At the time of its launching, it was the largest submarine in the world. Yet it was able to travel over 62,000 miles, consuming a chunk of uranium that would fit easily in a cigar box. For at the heart of this giant streamlined hull is the world's first nuclear power plant designed to drive a ship. Atomic power enabled the Nautilus to break by wide margins all existing submarine performance records. For example, our second picture shows us a view of polar ice taken from the 40-foot-long periscope of the Nautilus. In 1958, she became the first ship ever to reach the North Pole, traveling submerged under more than 1,800 miles of ice. The success of the Nautilus led, as we see in our third picture, to the building of other nuclear-powered subs. This is the Triton, almost 450 feet in length, much larger even than the Nautilus. This huge ship performed the incredible feat of traveling submerged around the world, almost 30,000 miles in 60 days. The enormous advantages of the atomic submarine had now been proved. It could move secretly and swiftly throughout the ocean depths for months, never having to surface or refuel. Difficult to find, even more difficult to destroy. If only the atomic submarine could launch atomic missiles from under the sea, America would have the greatest deterrent to aggression the world had ever seen. In picture 4, you're looking at the world's first ballistic missile submarine, the George Washington. It can retaliate instantly if an aggressor should launch atomic missiles at us. 16 Polaris rockets with hydrogen bomb warheads. This is the deadly cargo of the George Washington. Within minutes, they can become airborne and soar to targets up to 1,200 miles away. Now let's descend in picture 5 to the compact underwater world of a Polaris submarine. No foliage grows in this world, but it's a jungle of wires, tubes, 70 miles of cable, 24 miles of pipe, tens of thousands of intricate parts assembled in the various computers and systems that run the ship and launch the missiles. A gigantic electronic jigsaw puzzle. Our next picture shows us the man responsible for seeing that all the pieces fit together. At a signal from the White House, this man has the power to destroy millions of people. He must be capable of living with the constant tension of awesome responsibility. He must have intimate working knowledge of the nuclear reactor, the complex navigation system, the missile and launching mechanism. Years of sea duty, undersea warfare, and technical training are necessary to mold the commander of a Polaris submarine. But the skipper is only as good as his crew, and picture 7 introduces us to one of the men who must carry out his orders. He looks like the boy next door, and very well may be. That is, provided the boy next door has exceptional mechanical ability, a flair for math and physics, and a strong sense of devotion to duty. Only volunteers are accepted. Those who last through the rigid testing and screening period end up in such scientific training schools as that shown in number 8. A volunteer may become a nuclear plant operator or a missile technician, but he must be familiar with the other men's jobs as well as his own. He must learn about nuclear physics, reactor theory, celestial navigation. And now if you will turn the slide card over to number 9, we will see why a submarine is no place for those who suffer from claustrophobia. A Polaris sub has considerably more room than the World War II variety, but still it means over 100 men sharing an oversized sardine can with the deadliest weapon ever created. You wouldn't think it made for the easy, relaxed grins we see here, but these men have been chosen for their well-balanced personalities as well as their aptitude. They have a wonderful esprit de corps. Every man is a technician with an important job to do. Our next picture shows one of the most important of all. When you live close to an atomic reactor, there is the possibility of radiation leaks. That danger is reduced to almost zero by such radiation detectives as the corpsman we see here. He and 2 others assist the doctor in constant checks of the artificial atmosphere, the drinking water, or any material that comes close to the reactor. As a result of these precautions, the crew is actually exposed to less radiation than people on land. In number 11, we see one of the ways off-duty crewmen avoid boredom and the tension of close confinement. As well as providing the materials for aspiring artists, the submarine keeps a well-stocked library of books, films, magazines, records, and handicraft kits. A card game is usually in progress, and for working off excess energy, there's ping pong, and in the larger subs, a tiny gym. But picture 12 illustrates the most popular off-duty occupation. Slide rules compete with the traditional magazines featuring pretty girls for the Polaris sailors' attention. These men are serious students. They have available a full college curriculum of film lectures and books prepared by Harvard University. The men study such subjects as higher math, physics, computer theory, and history. They can actually get a Harvard degree while matriculating on a campus hundreds of feet underwater. And now we leave the human actors in our undersea drama. In number 13, we begin the story of the Polaris missile itself. This is an early test rocket, looking nothing like the final shape of the missile. Its purpose is to find whether a solid fuel rocket can be shut off in flight, thus controlling its range, enabling it to hit the designated target area. In 2 years of testing, more than 20 rockets of different shapes, there were many heartbreaking failures. But the bugs were finally worked out, and in April 1959, a rocket shaped like a champagne bottle climbed from its launching pad and made a perfect 300-mile flight. Polaris was successfully born. Now came the next step. In picture 14, we see a full-scale dummy of the Polaris being prepared for an underwater launching test. Igniting a Polaris for its flight while still in the sub would be far too dangerous. There had to be some way of ejecting it first, then igniting it. The answer came. It could be propelled upwards from a submarine tube by compressed air like a pea shot from a pea shooter. When it cleared the water, one of its rocket motors, such as the one shown in number 15, would ignite and send it soaring toward its target area. There are 2 such motors in each missile, one for each stage. When the first stage has exhausted its power, the second stage fires automatically, carrying the nuclear warhead the final stretch to its target. The 28-foot missile also has a navigation system, a fire control system, and a guidance brain made up of computers which will hold it on course. To make sure all the complex systems work together, we gave it a final launching from a tube set into the deck of a surface test ship. Our 16th picture captures the moment of launching, March 29, 1960. As the bottle-shaped Polaris shot up out of its tube in a cloud of vapor, the same question was on everybody's mind. Will it work? Is the Polaris a success? The mighty missile answered with a thunderclap as its motor ignited and it sped toward the South Atlantic. A perfect test. The age of the undersea missile was at hand. In our 17th picture, we're watching a Polaris submarine being loaded with its deadly cargo. That's the missile suspended from the cables at the right center. Lowering a Polaris into its snug-fitting tube is a delicate operation, a bit like threading a needle. Loading all 16 missiles takes about a week. But there's another kind of cargo, shown in number 18, which is just as important. Somebody once said an army marches on its stomach. There's little room for marching aboard a submarine, but if the crew is going to operate at the necessary peak of efficiency, good food is a must. A typical meal will offer a sizzling steak, French fries, plenty of vegetables, and fresh fruit. Feasts like this help make the months of undersea patrol duty more pleasant. And now in number 19, let's watch the George Washington head for the open sea and a rendezvous with destiny. The year is 1960. She will attempt the first launching of Polaris missiles from beneath the sea to a target 1,200 nautical miles away. At her heart, encased in a sheathing of lead to keep radiation from escaping, is her nuclear reactor. This provides all the power needed to drive, light, and operate the ship. At the top of our 20th picture, we see a land-based reactor used for research. Beneath the water in the pool are rods of uranium. The uranium atoms are constantly splitting and giving off heat energy in a controlled chain reaction. The reactor in our ship is indicated by the orange area behind the stacked-up missiles in the diagram at the bottom. It's designed as a kind of steel-jacketed furnace to contain the heat of the chain reaction. The heat is carried away by water piped through the furnace and used to manufacture steam. The steam is finally converted by turbines and generators into the energy that drives the ship. Number 21 shows us one of the huge gyroscopes so important to the operation of the ship. This one weighs 55 tons and is one of the largest in the world. It is used to keep the submarine steady. When its wheel is turned fast enough by nuclear power, it can counteract the force of rough seas or even the recoil of a missile firing. There are many gyroscopes of different sizes aboard. They're used for directing and keeping track of the submarine as well as guiding the missiles. But now, in picture 22, let's meet the pilot of our craft. You'll notice that the controls look a bit like those of an airplane. The pilot is even called a plainsman. There's logic to this. Below the surface, a nuclear submarine can dive, turn, bank, and climb like an airplane. And it's steered like a plane. Stubby wing-like sections on its stern and superstructure control its up and down movement. A rudder controls its direction. A streamlined hull and nuclear power enable a single plainsman to fly his 5,400-ton ship at speeds in excess of 20 knots an hour, faster than most surface ships. Of course, surface ships can see where they're going. Our submerged submarine actually has to hear where it's going. Picture 23 shows the sensitive sonar system, which makes possible navigation by sound. Sonar can detect sounds electronically and display what they reveal on a television-like screen. The technician in the foreground is watching such a screen. One kind of sonar picks up the sounds made by the propellers of surface ships or other submarines. Another kind sends out signals which are bounced off objects and then picked up again in a significant pattern on the sonar screen. Sonar can be used to pinpoint a possible enemy or target. It can reveal obstacles in the path of the submarine by bouncing sounds off them. In the murky depths of the sea, it's better than a pair of eyes. In number 24, we see the ship's course being plotted on a chart. In spite of the electronic wonder of the ship's inertial navigation system, it is a highly skilled man, not a machine, who is finally responsible for indicating the submarine's position. The red glow of this and some of the following pictures is caused by condition red. This is the use of a red-filtered light from sunset to sunrise. It makes it easier for the men to adjust to the normal night light of periscope and deck observation. And now if you will turn the slide card over to number 25, we'll see how our submarine can defend itself against attack. While her big guns, so to speak, are nuclear missiles, the ship has a full complement of the latest word in torpedoes to discourage enemies from getting too close. They are only fired as a last resort because this would reveal the sub's position. The primary purpose of the Polaris submarine is to remain undetected as a secret launching base for nuclear missiles. Picture 26 shows us the ship's attack station. From here, the skipper gives the command to fire the torpedoes or the missiles. The actual firing of a Polaris missile must be ordered directly by the President. This order must be received and confirmed by both the skipper and his executive officer. Then the captain relays the order through his intercom to the missile men in our next picture. The missile section is 130 feet long, and the tubes rise up vertically from the bottom of the ship like giant tree trunks. At the base of each tube is the compressed air launching system. At the top, the electronic brain which guides the missile to its target and the mighty warhead. Before the launching, the technician in picture 28 takes a final look at the navigation control panel. He is checking all the instruments that supply data to the guidance unit of the missile. The slightest error in the information fed to the brain can mean a target missed by many miles. If this submariner notices an error, he immediately throws the control switch which alerts navigation that corrections must be made before Polaris is launched. In number 29, we see what would happen if the command to fire were received from the White House. Polaris rises from the sea, and minutes later, a hydrogen bomb warhead explodes on target 1,200 nautical miles away. The first actual underwater launching of a Polaris missile, minus its nuclear warhead, of course, took place on July 20th, 1960. The countdown reached zero. A muffled boom came from the George Washington far below the sea, and our next picture shows the Polaris after being shot out of its tube by compressed air. Up toward the surface it rushed. After the missile emerged from the water, a computer near its tip had to give the automatic signal to ignite the first stage motor. If it failed, the missile would fall back into the sea. In number 31, we see what actually happened. The missile ignited with a crack of thunder, righted itself, and soared into the sky. Its second stage motor took it out of the Earth's atmosphere on a fast-moving trajectory that no known anti-missile weapon could intercept. At just the right second, a computer signaled the warhead to detach itself. It sped on its way like a fantastically powerful bullet, gradually pulled down toward its target area by gravity. 15 minutes after launching, the dummy warhead landed on target 1,200 miles away. Success. The dedicated work of thousands of American scientists, engineers, and industries had given us the most powerful weapon in history. In our final picture, the Polaris submarine speeds on its way, ready for instant retaliation. We will never start a nuclear conflict. There would be no victors in such a war. But if an aggressor nation knows we can destroy those who destroy us, it will be more likely to keep the peace. And in a world in which war has become unthinkable, what wonders the atom can bring. It can provide a cheap, unlimited source of power to light up our cities, irrigate our deserts, run our hospitals. Radioactive isotopes may release man from the diseases that still plague him. The potential is there. It is up to man to decide whether the atom will be used for death or for life.